moving on to section 6 of chapter 6. Wrapping things up here. Last time we talked about the law of sines. You must obey the law. This time it's the law of cosines. No prelude whatsoever. Hold on. Let's talk a little bit about a review here. Going back to geometry. Again, we were familiar. Didn't ask if you liked it. We're familiar with angle, side, angle, 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 side, or the dreaded angle, side, side. Those conditions require you to use the law of sines, which, if you just saw what I popped up there, it's much shorter, easier to use than this law of cosines. The trade-off is we have that ambiguous case. Okay, now for the law of cosines, dun, 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 it's a blue box. We're going to pay attention to this, but actually, you're just going to pay attention to one of those. You don't need to put all three of those in your notes because we can adapt. Okay, so, but let's take a closer look here. Notice we have the length of side C and the measure of angle C at complete opposite ends of our equation. We are going to use the law of cosines when it comes to side, side, side. That's going to be the trickier one. Well, the more tedious calculation, I guess. Or side, angle, side, that's going to be the easiest one. Okay. Now, as they're saying here, if we go back to, again, one of these things here, if that angle C happens to be a 90-degree angle, what's the cosine of 90? That's right, it's 0. So this whole thing here completely disappears because it goes to 0 and gasp! A squared plus B squared equals C squared. I've heard that somewhere before. I'm sorry, this one's a little messed up here. Construction company has been hired to build a tunnel. Yay, blasting with dynamite. An employee makes the measurements as shown in the diagram. How long is this tunnel going to be? Okay, so you can see here we have the measure of two sides and the included angle. This should remind you of side, angle, side. We're going to use the law of cosines. We don't know the length of segment AB. We do know the measure of angle C. So we're going to use this specific version of our law of cosines. We'll leave that unknown. We'll substitute the length of segment AC is 388 feet, square it. The length of segment BC is 212, square it, minus 2 times 388 times 212 times the cosine of our whopping 82.4 degree angle. Now at this point, if you trust your calculator skills, you could just type that whole thing in exactly as written. Come up with approximately 173,730.2367 blah blah. Hold on, that tunnel is going to be, wait a minute, that's in feet? 107, more than 173,000 feet. No, wait, look at the other side. That's the square of that length. Last step, Take the square root. All right, now that's something much more reasonable. 416.8, again, should be feet, or about 417 feet. Again, they gave us the two side lengths there. It looks like to the nearest foot, so rounding our answer to the nearest foot does seem reasonable. Now that 82.4, if you think about, again, the rules from geometry about triangles, that 82.4 is probably going to be the biggest angle. So segment AB is probably going to be the longest side. Sure enough, the law of cosines there bears that out. 417 is bigger than 388 or 212. So the side condition here, this is the harder one. Suppose that you were given this side is 5, this side is 8, this side is 12. Solve the triangle boils down to find the measures of all the angles. Okay. Oh, by the way, I'm going to try my best to be really, really diligent about this. Sometimes with the computer-generated problems, they forget about the whole triangle inequality postulate. Shortest side is 5. Next longest is 8. The sum of 5 and 8 is 13. 13 is bigger than 12. Yes, it actually makes a triangle in the first place. Check that just to be sure. Okay, again, sometimes with the computer-generated things, this is 5 and that's 8, and side C is 20, and not going to work. As it's labeled here, this is kind of the harder one because setting up our law of cosines, say we want to find the measure of angle A. So again, we're going to put the length of side A on one side by itself, and then the measure of angle A with cosine on the opposite end on the far right. Now, they go through and they do the algebra here to solve it for cosine A. Frequently, I will have students who refuse to go that way. So let's see, side A is 5, so we'll have 5 squared is equal to side B was 8, so we'll say that's equal to 8 squared, plus side C was 12, that's 12 squared, minus 2 times 8 times 12 times the cosine of angle A. So again, notice we just have the one variable there. We should be able to progress with the rest of it. Five squared is 25, 8 squared is 64, 12 squared is 144. Now be careful here, order of operations. All right, I've taken care of all of the exponents here. The 2 times 8 times 12 should give us 192, but that is still multiplied by the cosine of A. This is the biggest danger to getting these correct. Because it would be really, really simple. Okay, so we got the 25 over here, 64 plus 144, combining like terms, is 208 minus 192 cosine of A. It would be so simple to subtract those two and completely wrong. Because again, this is attached to our this is the variable term here. Here's a constant, here's a constant. The 208 and the 192 times the cosine of A are not like terms. You can't do that. We should then subtract 208 from both sides. But Mr. Mark, that's going to be negative. That's okay. The coefficient over here is negative. When we divide, negative divided by a negative will give you a positive. So the cosine of A is, well, 61 over 64 is 0.95312. Yes, that is a terminating decimal. And yay, the cosine there is less than 1. This angle actually exists. So when we do the inverse cosine of that, we should get a legitimate angle measure. Yay. Now, again, the way the authors go through and they say, all right, you solve it for this. Same values. Okay? So this is your choice. Welcome to America. You have some freedom. Yeah, don't get too cocky about it. But either way you want to go, if you solve it for the one variable equation, then we substitute nothing but numbers on the right-hand side. Or if we do the algebra stuff here, be very, very careful. Oh, it's so tempting sometimes. Make sure that you're combining like terms. There's one variable term in the whole thing. Either way we want to go, inverse cosine there, we'll find out that the measure of angle A is about 18 degrees. Okay? Now, I'll back up here. Boom, boom, boom. Is that reasonable? We found the measure of angle A is about 18 degrees. Well, sure. I mean, that seems like it fits. Side A is the shortest side, angle A, 18 degrees. That's pretty small. Do we get everything else to fit? Oh, wait a minute. Are we going to have to go through this again to find angle B and again to find angle C? Well, they're showing you the work here so that it works out. Oh, notice there. Please be aware of this. For cosine of angle C, again, they're doing it with their solve it first, substitute, simplify method. The inverse cosine of a negative number is obtuse. And again, as long as it's not too obtuse, that's perfectly fine. Or we could go with the easier version. Okay, again, the law of cosines, using the law of cosines is going to be valid with any triangle. You can use the method that they just showed you here of using the law of cosine 3 times to find the measure of all 3 angles. And we wouldn't have to worry about, ambiguous case or anything like that. What I'm suggesting is if we go back to the law of sines, it's shorter. We already know we're given all 3 sides. This is a legitimate triangle. We can use the law of sines now that we have the 18 to start off with and find those other angle measures. Okay? So sine of 18 degrees over 5 is equal to the sine of angle B over 8. Again, find our cross, well, just multiply both sides by 8. 8 times the sine of 18 divided by 5 will get us something pretty close to 1/2. The inverse sine of that gives us something that, hey, what do you know, pretty close to 30 degrees. I would say round to the nearest tenth, 29.6. Okay, now hold on. Sine of 18 degrees over 5 is equal to the sine of angle C over 12. Multiply both sides by 12. Take the inverse sine of 0.7416, blah, blah, blah. Oh, wait a minute. That's only 47. If we have one angle that's 18 and one angle that's 29.6, that angle can't be 47.9. Those three angles don't have a sum of 180 degrees. Go for the supplement. The longest side has to be opposite from the largest angle. The shortest side is opposite from the smallest angle. You take that 147 that we reject, it's got to be the biggest angle. It's opposite from the longest side. Find its supplement, and then things fit. Okay, so now that we've got law of sines and law of cosines, let's talk a little bit about, anybody want to be an airplane pilot? Do you want to get lost? Let's talk about navigation. Bearing is a very, very specific way of describing a direction. Bearing is always going to be given to you in a format that looks like this. That first thing they tell you there is either going to be north or south. The last thing they tell you is either going to be east or west. The middle is going to be an angle, almost always in degrees, telling you which way to go. So this bearing that you see there in figure 6, measured from due north, we're going to go 30 degrees to the east. Okay, so that's how you read bearing. Either we're measuring from due north or due south. We're going to go some angle off of due north or due south. And they're going to tell us if we're going east or west of that north-south line. So let's take a look at this. Pilot sets out from an airport and heads in a bearing. Here we've got a direction of north 20 degrees east. So not heading due north, heading a little bit to the east of directly north. Zipping along at 200 miles an hour. After 1 hour, he makes a course correction. It'd be nice to land at the airport. Adjusts his direction to north 40 degrees east. Uh-oh. Half an hour after that, dun dun dun, engine trouble forces him to make an emergency landing. We are challenged to find the distance between the airport where he took off and his final landing point, and then calculate the bearing from the airport to his final landing point. Hopefully, he landed safely, but we're going to send people to check him out. We need a picture. So from point A, the airport, hey, that worked out nicely for once. From due north, 20 degrees to the east. Okay? It said the plane was going along at 200 miles an hour. For that first part of it, heading it with that direction in that bearing for 1 hour, that would mean that's a distance of 200 miles. Pretty simple math there. The second part of it said it was half an hour after that course correction. So again, 200 miles an hour, half an hour. That's 100 miles. So you notice here the change in the bearing at point B is now again from due north going 40 degrees to the east. Point C is the landing spot. Play connect the dots. From point A to point C, here's our lovely triangle. Now the issue is the fact that, okay, we have this side is 200, we have this side is 100. They're asking us in part A to calculate the third side. Clearly not a right triangle, not Pythagorean theorem here. We could use the law of cosines if we knew the included angle. That would make it side angle side. Can we find that angle? When he makes that course correction, he turns 20 degrees to the right. So the angle between the two legs of the trip, 180 minus 20, is 160 degrees. Now, if you don't quite believe that, we could break this down and, oh, I don't know. Again, if this is 40 degrees here with each of our points here in our bearing, those are perpendicular. So if it's 40 degrees here, we could say that this angle is 50 degrees. This angle is 90 degrees. But what about this little thing here? Notice we have parallel lines cut by a transversal, alternate interior angles are congruent. So this little part of it here is 20 degrees, alternate interior angles. And then we can just add 50 plus 20 is 70, 70 plus 90. So this whole thing here is 160 degrees. Then we set up the law of cosines. Again, it's side angle side. We know the length of two sides and the included angle. Everything goes together on the right-hand side. So 200 squared plus 100 squared minus 2 times 200 times 100 times the cosine of 160 degrees. Again, that's the value for b squared. Take the square root. He flew almost 300 miles from the airport before the forced landing occurred. Okay. Now, the second question here was find the bearing from the airport to his final landing point. Okay. So we're looking for here. Oh, I'm sorry. Let me try and change this for once here. We're looking for this bearing now. Again, it's going to be measured from north. The turn here is to the east, but it's bigger than 20 degrees. Okay? As a matter of fact, if we could find the measure of this angle inside the triangle and add it to that 20 degrees, that would give us the angle of that bearing. And since it's the angle inside the triangle, we know two sides, we know the included angle. Well, as a matter of fact, we know all three sides. We could take the shorter version here and just use the law of sines. So the sine of that angle inside the triangle divided by, again, the side opposite was 100, is equal to the sine of 160 over the newly discovered 295.95. The sine of angle A is 0.11557, blah, blah, blah. Take the inverse sine. We find angle A is about 6.636 degrees. But again, that's this angle here added to the 20. So that gives us a total angle of rotation there of 26.6. So here is the bearing. North, 26.6 degrees to the east. Again, make sure that you're using that same format. Another application is area of a triangle. Now, hold on. You already know area of a triangle. Area is equal to 1/2 times base times height. But we've got the problem there that base and height have to be perpendicular to one another. What if you don't know this corresponding height that's perpendicular to this side? Never fear, trigonometry is here to help you. One way we can do it here is Heron's formula. Again, goes back to ancient times that people who know how to properly observe what's going on found that this actually works. Now we have this S here and here and here and here. Here's our definition. S is the semi-perimeter. You remember how to find perimeter. You add up the lengths of all the three of the sides, since we're talking about a triangle. So then for semi-perimeter, you just take half of that. And if we take the semi-perimeter times the semi-perimeter minus the length of one side, multiply that by the semi-perimeter minus the length of a second side, multiply that by the semi-perimeter minus the length of that third side. Wait a minute, we're multiplying 4 different lengths together. How is this area? I'm glad you asked. That's why we take the square root. Find the area of this lot. Businessman wants to buy a triangular lot on a busy downtown location. Yeah, lots of traffic there. This would be good. The lengths of the sides of the 3 adjacent streets are 125, 280, and 315. And man, somebody messed up the planning. That is not a right triangle. It's okay. We can still find the area of the lot. We start by finding the semi-perimeter. We'll add together the 125, the 280, the 315, divide that by 2, and oh, isn't that a nice number to work with? 360. So then Heron's formula tells us we'll take the square root of 360 times the quantity, 360 minus the one side of 125, times 360 minus the second side of 280, times 360 minus the third side of 315. So we could say that lot has an area of approximately 17,452 square feet. Don't need base and height to be perpendicular. Now again, this was not just thrown in here at random. Here's another way to find area of a triangle if you know the length of all 3 sides. See, it's side, side, side. This fits into what we've been talking about with the law of cosines. And that, as they say, is that. Please take a look at the bottom of the notes on OneNote for your assignment, and we will talk again soon.